We are now going to finish section 4.4, and we're going to go over linearly dependent and linearly independent. All right, the definition of a set that is linearly independent means the only way to get out the zero vector, the zero matrix, the zero polynomial, the zero whatever, is the trivial solution, meaning all of your scalars are zero. If there is another way to get out all zeros, then it is linearly dependent. So let's just look at this. So number 9 on the notes says A is the set containing the ordered pairs 1, 2, and 3, 6. So is this set linearly dependent or linearly independent? Well, if I did -3 times 1, 2 plus 3, 6, I would get out 0, 0. That means it is linearly dependent. There is another way to get out 0, 0 other than 0 times the first plus 0 times the second. Number 10 says A is the set containing the ordered triples 1, -2, 0, and -1, 2, 0. So this set, would it be linearly dependent or linearly independent? Hopefully you can see that if I just add the two of them together, 1, -2, 0 plus -1, 2, 0, I get out 0, 0, 0. Because it is all zeros is what I get out by doing something other than 0 times the first and 0 times the second. That's what we call the trivial solution. It is linearly dependent. All right, number 11. A is the set containing 0, 0, and 3, 4. Would this be linearly independent or linearly dependent? The answer is going to be linearly dependent because I can do any number you want. Let's pick 5 times 0, 0 plus 0 times 3, 4 would give me 0, 0. So that makes it linearly dependent. I did something other than 0 times the first one plus 0 times the second one gives me 0, 0. So something other than 0 times the first times 0 times the second gives me 0, 0, which means it is linearly dependent. All right, so from these, hopefully you can see if you're ever given a set of vectors where one of them is a multiple of the other one, it will always automatically be linearly dependent. Well, then now that doesn't always happen. So how do we determine this? So in the notes, I gave you testing for linearly dependent and linearly independent. All right, what we're going to do is, let me give us a problem here. Let's see, so number 12 says, is A, which is the set containing 3, -6, and -1, 2, linearly dependent or linearly independent? And hopefully we can see we're going to get out linearly dependent. But let's go through the process so we see how it works and what we're looking for. What we're going to do is we're going to put it into a matrix. Again, because we're dealing with vectors, we put them in as columns. And what are we looking to get out? We're looking to get out zeros. So now let's row reduce this. When I do, I get 3, -1, 0 over 0, 0, 0. What did I do? Row 2 plus 2 row 1. So going back to what we learned with our eigenvector information, all right, that's going to tell us my equation, -3x plus y equals 0, or -3x equals -y, or 3x is going to equal y. All right, so let's say x is 1, then y is 3. So if I did 1 times my first vector, 3, -6, plus 3 times my second one, I'm going to give out 0, 0. So because I have answers here, I have scalars that are not 0, 0. That means it is linearly dependent. All right, let's move on to 13. 13 says, is A, which is the set containing 1, 0, 1, 1, and 2, -1, linearly dependent or linearly independent? Let's do what we did a minute ago. So it's going to be 1 over 0, 1 over 1, 2 over -1, and I want to get out 0, 0. All right, well, when I row reduce this, I'm going to get 1, 0, 3, 0 over 0, 1, -1, 0. All right, so what this now says is my bottom row, my bottom equation, says y minus z equals 0, or y equals z. So I'm going to say y is 1 and z is 1. My top one says x plus 3z equals 0, or x plus 3 equals 0, so x is negative 3. So if I do negative 3 times my first one, plus my second one, plus my third one, I'm going to get negative 3 plus 1 plus 2, that's 0. Then 0 plus 1 minus 1, that's 0. So yes, using these scalars on the set I was given gives me the ordered pair 0, 0. So that is linearly dependent. I got 0, 0 out another way. All right, so number 4. 4 has A is the set containing the ordered triples 6, 2, 1 and negative 1, 3, 2. Would this be LD or LI? So put it into a vector, put it into a matrix. 6, 2, 1 over negative 1, 3, 2 next to 0, 0, 0. All right, then let's row reduce it. So let's see. I'm going to get 6, negative 1, 0. I'm going to rewrite it. I'm going to bring that bottom row up. So I'm going to do 1, 2, 0 over 2, 3, 0 over 6, negative 1, 0. All right, which is then going to give me 1, 2, 0, 0, so do negative 2 times the top. So 2 minus 2, 3 minus 4 is negative 1, 0 minus 0, and then 6 minus 6 is 0. Negative 1 minus 12 is negative 13, 0, which I can make this 1, 0, 0 over 0, 1, 0 over 0, 0, 0. So here I did row 1 plus 2 row 2. Here I did negative row 2. Here I did row 3 minus 13 row 2. Well, what does this tell me? This tells me my first scalar has to be 0. Should I call it x? Yeah, I'll call it x. And my second scalar has to be 0. So the only way to get zeros out is to do 0 times 621 plus 0 times negative 132, which makes this set linearly independent. There is only one way to get out 0, 0, and that is 0 times the first plus 0 times the second. And we are done.